So I think I may start. One more time, I would like to introduce myself. My name is Anna Semerzidi. I am the manager for corporate education in Toloka Academy. Today we will have a webinar on aggregation methods. I would like to introduce as well our speaker, Nikita Pavlichenko. He's a research scientist in Toloka. He will talk about various types of aggregation methods for different tasks such as classification, textual responses, and other. And as well, we will have at the end a practical part and also a Q&A, as always, when you will be able to make questions and we will answer them. Of course, as meanwhile, during the webinar, you can make your questions, ask your questions, and Nikita will answer them. So Nikita, I give the floor to you. You may start.
Yeah, hello everyone. Once again, my name is Nikita, and today we'll talk about aggregation methods. I have a brief presentation here. We'll go through it, and after that, we'll switch to the practical part where I will show you some code of how to use the aggregation methods. Okay, let's start with the motivation. So most crowdsourcing tasks rely on the overlap. You don't need it if your goal is to collect, for example, photos or to record videos, write short text, or something similar. These tasks don't have one true answer for the question. And it's, for example, a good idea to use post-verification here. But I advise to consider the overlap in most other tasks, for example, classification or I don't know, relevance or side-by-side comparison. So let's see how it does the aggregation work. And overlap. Okay, you assign each task to multiple performers and then aggregate their answers to the one true label. So this stage determines whether you get the most out of the resulting labeling. And aggregation is real science, but don't worry, we added some built-in aggregation algorithm in Toloka, and we wrote a Python library called crowdkit, so you don't need to code them yourself. To begin, let's consider a simple example. So it's a classification project where we want to label each image as a cat or a dog. For a given image, 3 performers complete the task. So the size overlap is equal to 3. And we want to use their answers to make the final estimate of the wisdom of the crowd. And the wisdom of the crowd concept suggests that we need to follow the majority. And this algorithm is called the majority vote. In this case, 2 performers think that there is a cat on the image. So the majority vote results in the single label, so a cat. And following this algorithm follows the intuition of the wisdom of the crowd that we must choose the most popular label to be the final answer. But there are some problems with majority vote. For example, can we account for the difference in performance abilities to improve the accuracy of aggregation? In majority vote, we treat each performer as equal ones. Yes, we think about performers that they're some people with equal abilities and equal level of expertise. But in real life, it's not always true. And there are some techniques to improve the majority vote and to get the better aggregation results. The simpler extension of the majority vote is a weighted majority vote. In this algorithm, we assign each performer some skills. These skills or we can call it quality. It could be, for example, the accuracy of the performer on your control tasks, or you can just assign some skills based on your own algorithm or intuition. But in most cases, these skills are just the accuracy on the golden tasks. And then you weight each response by this skill. And then you select the response with the largest weight, total weight. In this example, we have 3 performers, and we see that the total weight for the label cat is lower than the single weight for label dog. And then we choose the dog as the aggregated answer because this label was provided by the most experienced performer. Okay. So let's go a bit back and talk about how we measure the abilities of performers to complete the tasks. Yes, as I said before, we can compute the accuracy of performers on the questions with known answers, for example, controlled or golden tasks. And we mix these golden tasks with usual ones. And in this way, we can determine the percentage of correct responses for the project as a whole and the percentage of correct performance of individual responses for individual performers. And in general, the majority vote is a powerful tool. First, it's very intuitive. Majority vote is easy to explain to practitioner, even if they had no background in statistics or crowdsourcing or machine learning or anything else. You can even explain the majority vote to a child. And second, it's very efficient. The majority vote can be computed on huge data sets, for example, that consist of billions tasks. And it will take you maybe a second maximum. And last thing about majority vote is that in real life, it's quite accurate. That even if it is a simple algorithm, it performs well in practice. But of course, there are some more advanced methods that produce higher accuracy. Let's talk about the motivation. Why do we need some other methods? Instead of the weighted majority vote. The reason is that the most of the questions are not in the golden set. Yes, for example, you might label, for instance, 100 tasks as the golden ones, but can we use all of the tasks to estimate abilities? And it could be done with some advanced methods, such as Dawid-Skene algorithm. This is a very old method proposed by Dawid-Skene in 1979, and it works like that. Let's consider an example. In this example, we have a small data set with 4 images. Our goal is to classify each image as a cat or dog, as in the previous example, and we recruit 3 performers. And each of them labels all 4 images. In this example, we do not have golden set questions. So how shall we aggregate the responses? And the Dawid-Skene algorithm simultaneously finds answers to the questions and abilities of the performers that agree with the observed data the most. It may sound challenging, but let's try to work it out. These labels and abilities don't look quite right for the data, yes? Let's try, there's these abilities that and labels that we see on the slide. Why? Because we see that the cat maybe is more likely to be the aggregate label, and here's dog more likely to be the aggregate label, and this last cat also doesn't match the majority, So let's try some other ones. Let's consider this list of abilities and this list of labels. Here, second and third performers have an ability of 1. And the answers are aligned with the answers of strong performers. And this looks much better. In real life, all the abilities and labels are optimized simultaneously by something called exploitation maximization algorithm. But we won't go deeply in the details of the implementation. Just remember that there are some optimization methods that find you the best abilities and best labels. And Dawid-Skene has some benefits. First, it's pretty general. This method works under a more realistic model of performers with different abilities, because the model of the majority vote is not really realistic. And the second, it's quite efficient. It's fast enough. Of course, it is slower than the majority vote, but it's fast enough to be run on the huge data sets. It's very practical because it uses all the questions, and it's accurate in most of the experiments. It often outperforms the majority vote. And we have covered all the aggregation methods available through the Toloka interface. Maybe you saw the Dawid-Skene algorithm in the interface, and I bet you saw some aggregation called aggregation by skill. And this method is just the weighted majority vote, where your weights are the skills you provided. So we have only 2 aggregation methods in the Toloka interface, but we have more aggregation in our Python library called crowdsourcing. Let's go through them. The first method I want to share with you is GLAD. This method estimates the abilities of performers, and it also estimates different difficulties of the tasks. This is not some real estimates of difficulties. It's just a sample that just an example. It may not be the true for this data set that is on the slide. But it tries to estimate some difficulties, and if the method decides that this task is difficult, it decreases the abilities of the performers. So it tries to think that for difficult tasks, people usually have smaller abilities. And we have implemented some improvements on the majority vote. The first method is something called WAVA. It's weighted average. It does 3 steps. First, it aggregates the responses by the majority vote. At the second step, it tries to estimate the skills. It estimates the skills as a fraction of votes that are similar to the majority vote for each performer. And then it does the weighted majority vote with the weights estimated on this second step. And we also have the zero-based skill algorithm. It just repeats the second and third step until convergence. So it just repeatedly estimates skills and does the weighted majority vote. And these are all the methods that we implemented for the classification tasks, where performers choose only one provided option. But we also implemented more advanced methods for different types of tasks. For example, we implemented aggregation methods for pairwise comparisons. Do you maybe use pairwise comparisons in your projects, guys? I hope that I can somehow communicate with the audience. So just type maybe no in the chat if you never run project with pairwise comparisons.
Yeah, we do use pairwise comparisons. And
yes, that's cool. Thank you. And if you use pairwise comparisons, maybe you use it for the following setup. You have some items, for example, on the web pages, and you want to rank these items. And to obtain the ranking, you make the crowdsourced pairwise comparisons. You ask crowdsourcing performers to compare a pair of items. Let's consider this example. We have 3 items, and we ask performers to compare, for example, A and B. And this performer, the first performer, chooses A over B. The second performer chooses B over C, and the last one chooses C or A. And we have this list of comparisons, and we need some aggregation method that will construct our ranking, because we cannot do anything with just the comparisons. And an example of the pairwise comparisons aggregation method is the Bradley-Taylor model. What does it do? It tries to estimate some score for each item, and this score is based on your annotation, so based on your comparison pairs. For example, it for the item A, it estimates the score as 10. For B, it's 5, and for C, it's 2. And it follows this probabilistic model. We assume that the probability of A to be ranked higher than B is this fraction of scores. It's fraction of the score of the A score and the sum of the scores of A and B. And in this example, A should be ranked higher than B with probability 2/3. We also implemented the aggregation methods for textual data. Let's consider an example of project where you collect some textual data. For example, you run the crowdsourced audio transcription task. And in audio transcription, performer's task is to write some text. Yes. And let's consider that each task is completed by multiple performers. And each performer writes some text. Here on the slide is some example, some 3 texts written by performers. And all these texts are slightly different from another. And we also need to somehow aggregate these responses. And there we use some text aggregation methods. The simplest one is rover. It just aligns each text sequence and simply does the majority voting on each word or each token, if your tokens are not words. And then you obtain the aggregated text. And the last method we will cover today is RASA and HR RASA. They are methods that make use of some deep learning methods. Firstly, they took some texts provided by performers, pass them through some neural network, and get the vector representation for each text. And then it chooses the best vector by estimating the performer skills, like we're doing, for example, in Dawid-Skene, and then transform this best vector back to text. So that was the end of the presentation. Any questions so far? yeah, please feel free to stop me anytime to ask some questions. Yes. So I think in this case, we can proceed to the practical part. I'll stop the sharing for a second.
Yeah, I think if anyone have any question, please feel free to type it in the chat box or unmute yourself.
Mhm.
And yes, and also, of course, we can answer your questions later if you want the end of our session.
Yes, and we will do these comparisons just in several minutes right now. Yes. So let's start. Yes. In this practical part, we'll check the aggregation methods on 3 different tasks. We will start with the classification project, and we'll assume that we have some text sentiment analysis project. And the performers should decide, is it text positive or is it text negative? And we collect the responses from Toloka and we want to aggregate them. And we download the TSV file with our annotation from Toloka and just load it to Pandas data frame. You may know that there are some strange columns that you download from Toloka. In this case, we have the input text. It's our input we use in our project. It's just the text performers need to classify. The output result is the labels provided by performers. Golden result is golden labels. And we have lots of the information here. And we'll only look at one more column. It's called assignment worker ID. It is a unique identifier of the performer. So to use the aggregation methods from CrowdKit, we need to transform this table to the following format. We only need 3 columns. It is some task. The first one is some task identifier. In our case, it's just the text we have given to our performers. The second one is the column containing performer identifiers. In our case, this is assignment worker ID. And of course, we need labels provided by our performers. Okay, let's take only these 3 columns from our data frame. And then we need to rename them to have the following names: task, performer, and label. Okay, so in this project, so yes, I'm here I will just encode the text to some identifiers because it just looks bad in the notebook. It's not convenient to use the old text, so we'll use the IDs here. And this is actually the famous machine learning data set called IMDb movie reviews. So for this data set, we can measure the aggregation accuracy. So in real life, we cannot do this. And below some just functions for measuring the accuracy. So let's start using the aggregation methods. First, we need to install the CrowdKit library, obviously. Just run pip install CrowdKit and it works. And then let's import some aggregation methods. We'll compare the majority vote, Dawid-Skene, and Glad here, but we can also import some other nodes. Okay, done. First, let's run the majority vote. To run the aggregation methods, we create the instance of the class of the methods class. Here is just the majority vote. And we run the fit predict function, just like in scikit-learn, for example. Just run the fit predict method of the aggregator and pass this data frame to it. And we'll get the result of our aggregation. Let's look at it. Yeah, for each task, we now have an aggregated label. We can also predict the confidence for each label with the fit predict proba. Proba means probability, obviously. And we'll have some probability distribution or the model's confidence in the aggregate label. In case of majority vote, it's just a fraction of performers voted for this label. For example, for the first task, all the performers voted that it is a positive text. But we can see that for this task, one of three performers voted for negative, and two others voted for positive. And let's measure the accuracy of the majority vote. Yes, so it's about 0.82. Okay, this is a baseline. Let's try Dawid-Skene. This is just the same code, but we replace the majority vote with Dawid-Skene, and there we pass the number of iterations. Because, as I said before, Dawid-Skene is an iterative method that runs the expectation maximization algorithm. And we need to decide how many iterations we need to run this EM algorithm. And we'll do the same. We can see that it takes a bit more time, but it's also pretty fast. And let's measure the accuracy. And we can see that Dawid-Skene performs a bit better. Yes, here we had 0.82, here we had 0.85 maybe. It's much better for the classification. So 3 points of accuracy is a good increase. And we can also get some useful information that Dawid-Skene algorithm has discovered. For example, it estimated the distribution of our labels in the dataset. Here we can see that Dawid-Skene estimated that, that there is 45% of negative labels and 55% of positive labels. Okay, this is great. And also, he estimated something called performance confusion metrics. So it could be difficult, but in the presentation I said that Dawid-Skene tries to estimate a single number, some skill of the performer. But in real life, it's not true. It tries to estimate a bit more difficult thing. It estimates the confusion matrix. This matrix has this information. Each column of matrix contains the probabilities of the performer's answers if the true label is this. For example, this column says that this performer will answer the positive if the text is really positive, and will answer negative with this probability if the text was positive. But if the text was negative, the performer will always answer positive. So in case of the negative text, this performer also all the time will be wrong. Is it clear, or I should explain a bit more in details? Yes, the question, how do you make sure that Dawid-Skene converges within 50 iterations? Yes, we're not sure. And so we have not yet implemented some kind of the convergence criteria. Yes, yes, there is some metric called evidence lower bound and maybe, and these, and we should stop the Dawid-Skene algorithm when this quality metric doesn't change for several iterations. And it is not implemented right now, but it will be implemented maybe within a week or two. So our team is working on it. So yes, it's really true. Maybe yesterday I saw a comment with with the convergence criteria for all the algorithms. Yes, but right now in the CrowdKit 0.0.8, we don't have the convergence criteria, but we should work on. So okay, and now let's try GLAD. So it is very slow algorithm. So I run it for, I did a single run of this algorithm, and it took me 3 minutes. It's not maybe a long time, but in our tutorial, let's not wait 3 minutes because anyway, nothing will change. And GLAD gave us the accuracy of 0.84. Yes. And it's higher than the majority vote. Yes. But it is a bit lower than the Dawid-Skene produces. It's better than the majority vote because it's taking into account performer skills, but it's worse than the Dawid-Skene because it's single coin model. It's what means single coin. It doesn't estimate the confusion metrics, it estimates the single number for each performer. And let's look at these numbers. The alpha's property shows the estimated abilities of the performers. They are unnormalized. So you can see some negative numbers here, or numbers that are larger than 1. But if we take the sigmoid of these numbers, we'll get the probabilities. But you can think about this number that if this number is larger, it means that the performance is better. And it also estimates the difficulties of tasks, task difficulties. This parameter is called betas. And in fact, these are inverse difficulties. And it means that larger the number, simpler the task. And we see that the third task was harder than the first two. Okay. So if there are, maybe you have some questions so far. If no, we can switch to the pairwise comparisons. Okay. Feel free to stop me. Okay, so let's move on to the pairwise comparisons task. Now let's consider the side-by-side comparison task where our performers need to select a picture of an older person between these two. And we aggregate this comparison and construct the ranking by the people's age. First of all, let's download the dataset. And this is our dataset from our paper. So yes, there is a question. So when do you think we are okay with majority vote Dawid-Skene, and when we need to go to GLAD? What are some indications that application is not enough? Yeah. So actually, I never saw an example where GLAD performed better than Dawid-Skene. So it is very popular method in the crowdsourcing research, and for this reason we have implemented it. But in real life, I never saw when the GLAD performed better than the Dawid-Skene. And what are the indicators that just simple aggregation is not enough? Some indicators. Simple aggregation could be not enough if you see that the task is quite difficult. For example, if all the performers complete the task perfectly, and you can see this, for example, when you look at the golden set accuracy, you can aggregate the results with the majority vote. But if you see that performers have some difficulties with your task, it would be better to use Dawid-Skene. Maybe you can try GLAD if you're sure that there are some more difficult tasks and there are some significantly less difficult tasks. You can try it. You won't get any significant decrease in quality comparing by Dawid-Skene. Hope I answered your question somehow. Okay, that's great. So let's move on to regulatory. Okay, we have downloaded the dataset, and this dataset is from our paper, so it is already in the necessary format. When we aggregate pairwise comparisons, we need the following 4 columns. The first 2 are left and right. It's some identifiers of left object and the right object. The third column is label. It is the identifier of a performer's preference between these 2 objects. So if performers chooses the left image, there should be a link to the left image. And performer is as in classification is just the performer identifier. And we're going to use the Pavlichenko model for aggregation of pairwise comparisons. Okay, it's also a heavy model, and in this example we run lots of the iterations. So let's just skip the weighting part and use already trained model. As the result, the fit predict method of Pavlichenko gives us the scores for each object in your dataset. And we can obtain the ranking. Just sort these images by the estimated scores. And as I said in our presentation, we can find the probability, for example, that this left person is older than the right one. This is a long line of code. I can split it. We just make use of the formula from the slide. We take the score of the left image and divide it by the sum of the scores of left image and right image. And as a result, we get that the person on the left photo is older than the person on the right photo with probability 0.99. That's cool. Any questions so far about pairwise comparison aggregation? Okay. Let's move on to the textual responses. First, let's download the dataset. This is also the dataset from our paper from New Reefs. This is a dataset of crowdsourced audio transcriptions. And in this task, each performer will ask to transcribe some audio file. And each audio file was transcribed by 7 performers. So we need to run some aggregation algorithm to obtain a single transcription for each audio file. Okay. And when we run aggregations for textual data, we need data in the following format. We need the column with some task identifiers. As for the classification, we need the performer identifiers, and we need some text. Yes. Let's run rover. Okay. I will show you how to deal with rover because it's most it's the most common method for the textual response aggregation. Because, for example, RASA and HRASA and more advanced methods, they require the data to be, for example, grammatically correct or just some making sense English text. And Rover doesn't need the data to be some useful and meaningful text. It can be any sequence of characters. So let's run Rover. To use Rover, we need two functions. The first one is called tokenizer. This is the function that just splits the text into words. And we need the tokenizer. It's a function that joins the list of words back to the text. In this example, we use very simple tokenizer, just split text into words by the space. And the tokenizer is also pretty simple. We'll just join the words by spaces. And let's run over. It's pretty fast method. It will take us maybe a minute to aggregate this data set of crowdsourced audio transcription. And as the result, we get the text for each audio file. So it worked. Yeah, so any questions so far? So we are coming to the end of our webinar. Yeah, difference between Bradley-Terry and noisy Bradley-Terry. The noisy Bradley-Terry is more advanced algorithm of aggregation of pairwise comparisons. And it takes into account the performance reliabilities, like we do in the Dawid-Skene. Yes, there is a paper. I don't have it just right now, but I can send you a link if you're asking to. It is developed in Toloka by Valentina Fedorova. Yeah, I'll send it to you. Yeah, but I didn't show the noisy Bradley-Terry because the CrowdKit implementation, occasionally it has a bug, and so it produces bad results. And when we fix it, yes, yes, you can use the noisy Bradley-Terry. But yes, I made some experiments with noisy BT and usual BT, and noticed that maybe noisy BT produces just a bit better results, but not completely better. So my advice on choosing the aggregation methods. Usually, when you have some classification project, it's okay to run the Dawid-Skene. So most of the time, it performs pretty well. Yes, I'll answer your question just in a second. But if you have very little amounts of data, it's better to use the majority vote, because if you don't have lots of data, it's difficult to estimate the parameters for the performance. Yes, for example, in the Dawid-Skene algorithm, we need to estimate the number of label squared parameters for each performer. And for instance, if we have 10 classes in our classification, we need to estimate 100 parameters for each performer. And we need a lot of data to do that. So, and if your pool maybe consists of less than several thousand tasks, it's better, maybe it could be better to use the majority vote or weighted majority vote. So yeah, so it's cool that there are some questions. Yeah, can you show some examples when rover aggregation doesn't work as expected? What does it mean, work as doesn't work as expected? So could you please clarify a bit? Do you have any aggregated practical some issues in aggregation? Yes, there could be some issues in aggregation because we just do the majority vote on tokens, and the resulting text can be not a meaningful English text. But maybe I don't have. Yes. But I don't have maybe a good example. But we can do something. Example. I don't know. Just no, I don't have an example. But if you do the audio transcription, your quality metric is word error rate usually, and the rover aggregation significantly decreases the word error rate comparing to the mean wear of the audio transcriptions. So just based on the machine learning metrics, rover aggregation performs very well. But yes, it can broke your text and make the text not meaningful. So perform compared to L1, L2 head app. L1 generates labels and picks the best. Yeah, we have run some experiments with, yeah, let's start with L1, L2. Am I right that you're talking about the post acceptance or something like that, when you just ask performers to write the text and some other performers pick the best text based on response? Yes. We run the example, some simple experiment when we asked performers to choose the best transcription themselves. And it was quite good, but the resulting quality was a bit lower than the rover. So rover performs a bit better than people in aggregation, in text aggregation. And you can check out our paper, and we even trained a neural network to summarize the transcriptions, and it even performs better than rover. We actually trained the T5 on our data set. Yes, there were some question.
I think, Nikita, there was one more question.
Yes.
Nikita.
Yeah, from Nikita. Yes. Do you have any aggregated practical comparisons of methods like this and bear in 80% of tasks? What is delta? Example. Yes, there is a paper and that compares the aggregation methods. Inference and crowdsourcing. Sourcing is the problem solved. From YODB, yes, this is the link. Yes, you can check this paper, and there is a big comparisons of the aggregation methods. Check out table 6. And here we can see that the Dawid-Skene performs better than the majority vote in maybe in all of the tasks in the comparisons by genre. So, but yes, there could be some examples when the Dawid-Skene performs worse than the majority vote, but it happens very rare. Okay. Any more
Yes,
questions?
yeah, we have more some 8 minutes until the end of our session. Is there any questions? Maybe you can unmute yourself if you want, or type your question in the chat box. So let's, I think, ask Nikita.
Oh, yes. Toloka seems to use naive bias variation for dynamic overlap. Why does it use that? Yes, this method seems to be similar to weighted majority. You can estimate confidence for each option by using performer skills and then choose the one with maximum confidence. Why does it use most popular response and not the remarks? So the dynamic overlap just does the weighted majority vote, and then it estimates the confidence in the weighted majority vote label using the single coin Dawid-Skene model. It's not about, it's no, yeah, sure.
Yeah, the question is like why does it estimate like it can estimate confidence for each label basically.
Mhm.
What is the confidence of each of the labels, and then choose the one with maximum confidence instead of
Mhm.
choosing one with weighted majority or with whatever method and then estimating its confidence.
Yeah.
So why shouldn't we use like Argmax in this case? And maybe there are some reasons.
Yes. So the question is that if we estimate the confidence following the single coin Dawid-Skene, why we don't just aggregate these labels with single coin Dawid-Skene, but we do the weighted majority voting? Yeah, it's a good question, and I'm afraid that I don't have a good answer here. So yes, I don't have a good answer here, and it is a good question. I can ask my colleagues, but I don't know.
Thanks.
Yes, but yes, it is a cool question.
Yeah, so Nikita, we can ask our colleagues and get back to you with. I will email you with an answer of your question.
Okay, yeah, thank you. And like just like curious why it's not in CrowdKit, but it's probably related to that. So if there
naive bias, yes, we're planning to implement the single coin Dawid-Skene, and it would be pretty similar to naive bias. So
okay.
In the E step, it just naive bias.
Yeah, thank you.
Okay, so maybe any other questions for the end? Maybe, can I ask a question, Nikita? So could you please tell me how to choose in each method the number of iterations?
Yes, I've covered the question, but I can repeat it one more time. So usually, right now, you can feel free to put very large number here. So 100 iterations is enough for the expectation maximization algorithm to converge. And it won't take long time for you to wait until the aggregation is done. But we will soon implement the conversions stopping criteria, and you maybe won't even need to choose the number of iteration. It will be just predefined, and it will stop when it converges. Hope I answered your question.
Okay, yes, Thank you. So I think that since we don't have any other questions, and we have like 2 minutes before the end, I would like to thank all of you for joining us today. I hope you found interesting our session. I would also like to thank Nikita, our speaker, and I would like to say that we will share a recording of this webinar with you, and also we will keep you posted for our upcoming webinars this month. And if you have any other questions, of course, please email us. And for Nikita, to whom we didn't answer, we will answer his question by email. So great. Yes, thank you very much again, and have a very good day or evening.